some point in between all of this, also he was working, he said, at NASA and Lockheed Martin, and then he was a professor at Montana State University before he joined the faculty here at GSU in 2014. He still commutes a bit between here and Montana, apparently. And he's also been very successful in getting grants from both NASA and NSF, and in particular here, affiliated with GSU and the Computer Science Department, he's also worked on this informatics.
Informatics.
I think I put an extra syllable there.
Don't worry about that.
Center. So he's going to tell us a little bit more about the work he does related to the sun today, and so please welcome.
Thank you. Thank you for inviting me here. So, where was I going to? Oh yeah, I also work for the European Space Agency. So the sun also rises. I wonder, this was widely known as Hemingway's best book. It was also his first book. It's kind of depressing if your first book of your first paper is the best one and it's only downhill after that. But nevertheless, I actually like For Whom the Bell Tolls better. I wonder how many of the grad students here have read Hemingway? A few, okay. That's good. I highly recommend it. Oh, one move. What's going on here? It's frozen. Even the escape doesn't work. All right, shoot. Is this because of this thing?
Take it out if it doesn't work,
Yeah.
If it's causing the problem, just take it out.
No. Okay, well, I'm afraid. I can't even do that. I can't even do that. My mouse isn't working. Oh, good. Yeah. No, it's gone again. Ah, there you go. Good. Now the mouse is back. Thank you. I'll find it. Yeah, in a minute. All right, good. There we go. Play slideshow. All right, so as I was preparing this, I discovered that the main theme of my research is magnetic fields. And I'd like to give a little quote of a famous fellow countryman, Hendrik van der Hulst. Magnetic fields are to astrophysics what sex is to psychoanalysis. So if you learn more about magnetic fields, you can learn more about sex. So let me begin with some observations. This is what we call the everlasting eclipse, an observation by a coronagraph on the SOHO spacecraft. Little circle in the center is the sun, but it's blocked out so you can see the background. And this is about a month's worth of data. You see the background starts moving. And what you notice right away is that it's incredibly active. There's just a lot of expulsions going on all the time. And sometimes these expulsions don't go sideways, but they come straight at you. And that's what's going on here. Look at that. There it goes. So this looks like a giant mushroom blowing up and coming straight at you. When that happens, you can have problems on Earth. So as a result of one of these, in about 30 years ago already, there was a magnetic storm that collapsed the entire power grid in Quebec and burned up electrical connections all the way down the East Coast in the US. And here what you see is a transformer, a giant transformer. That the power comes from Hydro-Quebec, is brought to the East Coast as clean power. Totally burned up. And these things you cannot go to Radio Shack and replace. they're built to order, take a couple of months to replace them. So if there's one or two down, then they can route the power around it. If a whole bunch of them breaks down, then the whole grid breaks down. You don't want it to happen. As a result of this and many other events, some presidential committees started investigating this. The first under the second President Bush, was completed under President Obama. They came with a report, but let me show what the effects are. Space crew safety. High energy particles accelerated in these events can actually kill astronauts and at least cause cancer. There was a big one during the Apollo flights, during the era of the Apollo flights to the moon. They didn't have a way of predicting it then. They just missed it by pure luck. So it could have been that two astronauts on the lunar surface would have been fried if they had been there. It was in August 72, I think. Aircraft that go over the poles, a lot of them now, have to be rerouted because the high energy particles come in over the poles, called polar lights, and they can lead to unacceptable levels of radiation. Radio signals and navigation devices get distorted. My students, this is what they get most upset about. What, my cell phone won't work? Big solar flare, yeah, correct. And you do damage to communication satellite and then the geomagnetically and this current. But they also do beautiful things. Here you see the polar lights seen from the space shuttle, and they're incoming high energy particles that interact with the atmosphere, ionize oxygen and nitrogen, and that's why you get the green and blue and red light, which is truly beautiful. So here is a simulation of what was the largest solar event ever, the 1859 Carrington flare.
Charged particles would travel close to the Earth. The sun's magnetic field, carried in the plasma of the solar wind, flows continuously by the Earth, distorting the planet's field and pulling it back.
So what you see here is reconnection.
The red illustrates the higher density plasma, which forms the magnetopause, the boundary between the magnetic influence of the sun and the Earth. The wind also forms a lower density magnetotail behind the Earth, represented by blue in this computer model. This process is happening all the time as the solar wind is constantly flowing by the Earth. But a coronal mass ejection, or CME, can change things. The higher density the stronger magnetic field carried within the CME strikes Earth's field and significantly alters the structure. Here we see the dramatic changes in Earth's magnetic field and the shape of the magnetopause as the CME passes Earth. But close to Earth, the magnetic field is largely unchanged. Earth is protected from the intense solar event. This is the case for a rather ordinary CME. In this example, a CME launched by an X3 flare from December 2006. But what would happen in the case of a more intense event, such as the Carrington event of 1859? With the aid of similar computer models as before, we can explore some of these possibilities. Here, a much stronger CME compresses the magnetic field between the sun and Earth and generates more density in the bow shock, represented by darker red. The front of the magnetopause is pushed much closer to the Earth than usual. Even the fields and plasma trailing behind the Earth are more strongly distorted.
Okay. So 1859 was the largest one ever, and according to newspaper reports from those days, you could actually read the newspaper in the middle of the night in New York City because of the polar lights, not the polar lights, the aurora. And they saw it all the way down to Cuba, the aurora, which never happens again. So this is a flare that, according to our estimates, happens about once a century. We haven't had one since 1859. I'm not going to tell you that one is long overdue because you know that's not how statistics works. But once in a century is something to think about, at least. You want to give a good warning and you can take protective measures, just like you would as for hurricanes or earthquakes. You can't stop it, obviously, but that's not the objective. The objective is to protect our technology. In 1859, they had telegraph lines, and they all started rattling by themselves because of the induced currents on the long lines, which made them active. They didn't have much high tech at the time, just steam engines, which are not affected by solar flares. But now we do. So there's a national effort now, started under Obama and gone under the radar so far in the current administration. Hope it stays that way. So quite a bit of money is going in there to try to make decent warnings, and universities are invited to take part in that and take protective measures for the grid. So for example, you can put big capacitors on transformers to help them protect against DC currents. So the work that I do is related to that. And one of the things I've been working with also with Rafal already back at Montana State was identifying objects on the sun. These are actually ground-based data, H-alpha. And the dark structures are called filaments, for obvious reasons. And these are the things that actually drive these coronal mass ejections, like that Carrington event that I showed you, and the CMEs that I showed you in the earlier movies. So these are the origin and the cause of these eruptions. They're basically the outline currents in the solar corona. So this was part of a big NASA project where we got the assignment to develop identification feature tracking software for these kind of phenomena. And continuing with that, Aparna and I have been looking at these events. And first thing I ask you to look is look at the component of the magnetic field on the sun in these filaments, and compare that to the component of the magnetic field as it reaches the Earth from the eruption. Because there are two different, it can be up-down in the north-south direction, and can be down-up, south-north. And only in one case do you get reconnection, and in the other case, the eruption is harmless. So about half of the eruptions are harmless from the start, if you only knew. So which one is the dangerous one, Aparna? The southward, right. So she started looking at it, and I was totally surprised because it was a big result first time around. There were this is about a decade's worth of data. And we found if the filament field was north, then the IMF, interplanetary magnetic field, was north too. So those are the harmless ones. Same good correlation with southward, and just a few that are different, which maybe is ascribed to interaction between different CMEs. But this is a good predictor already, just from a small research. This is not big data, obviously, just old-fashioned hand-done data analysis, because there aren't so many events here. So these measurements are done at L1, and the solar measurements are done from the H-alpha data, and Aparna did all of that work. A nice result, a good result. In general, there is an incredible amount of missions currently available to get data from, not just in heliophysics. There's a similar chart for astrophysics. There's one for planetary physics. And what you see here, these are all spacecraft. A few of them, most of them are NASA. A few of them are joined with other agencies like SOHO, GeoTail, Solar Orbiter, and Hinode. They all have US presence also. I don't know what gold is even. And one of the challenges now is when you're trying to analyze an event, you could get data from all these satellites, and you have to start getting to know the data formats, where to find them, how to compare them, and so on, which involves quite a bit of work. But it must be done. In general, though, we started doing automated feature recognition a long time ago. This graph is at least 10 years old. What you're seeing here is for solar missions, and you can do the same for astrophysics missions, very similar graph. The lifetime data volume in petabytes, so the total archive of data. So this is 1 petabyte. And the start year of the mission, and here are the names. And then the radius of this blue circle is the logarithm of the data rate. So if you look at ATST, which is now the Daniel K. Inouye Solar Telescope being built in Maui and having first light very soon, gives an incredible data rate and will have an incredible data volume. This is NFS funded. SDO is the Solar Dynamics Observatory, flagship NASA mission with also incredible amount of data. Just it dwarfs everything. The SDO archive can set 5% of its memory aside to contain all the other solar data that exists at the moment before ATST. And the same is happening in astrophysics. So we had this SDO feature finding team because it would be too hard to analyze these data by eye. And here you see one thing. These are solar magnetic fields, and the green squares are where field is emerging, so where you see new field coming up with the two polarities. And you can imagine this is doable by machine. If you give a poor grad student to do this, they'll very soon find another advisor. Because this is just hard. It's small. These are important. Emerging magnetic fields are very strongly related with eruptions and flares, so it's important to know about them. Here is one of these emerging fields zoomed in upon, and what you see, the yellow are the polarity inversion lines. That's where the polarity switches sign from plus to minus. And right in the middle of this active region here, you see the flux emerging. These red lines are where the shear of the magnetic field is large and where a flare is likely to occur, and flares did occur here. So this is a nice first result to give an early warning. So we have a lot of data now, and in order to analyze a lot of data, you need to have people who know how to do that. We're not really specialized in that as astrophysicists. Computer scientists are, though. They've looked at humongous databases. So we have this group here that Rafal and I started with. It's called the Solar Stellar Informatics and Imaging Cluster. Stuart plays an important role in it. It's truly interdisciplinary. We sit on each other's committees for graduate students. The graduate students work together to solve problems. We have a weekly meeting chaired by Rafal where we talk about problems, give presentations, and so on. And it's been really fun, actually. So I'm giving you one example now of the research we do, rather than a general description or trying to put everything in a bullet list. So high-energy protons from solar flares can be lethal for unprotected astronauts. And we're going back to Mars, or we're going to Mars, we're going back to the moon. And so astronauts will be outside the protective magnetosphere of the Earth for long times on end. And they'll be susceptible to these protons, high-energy protons. Now, when they're inside the spacecraft, that actually gives a fairly decent protection. It makes the radiation level go down by a factor of 10. When they're outside, extravehicular activity, or they're walking on the moon or walking on Mars, they're unprotected. And that's the first thing that the NASA people want to know about. So this is what happened. You get these CMEs, you saw the images, there are ions and electrons coming out. The electrons go faster. And here's the radiation hazard. And they propagate roughly along the field lines. So you can see them coming. And the question is, can we protect those? Well, Sukaina, who's a computer scientist, he's here, has been working on that with several of us. So I'll give you a machine learning approach to this issue, although we don't really have enough data. We have curated 47 solar energetic particle events with enough information in a 10-year interval. These are observed in near real time with NOAA's GOES satellites, which are specifically designed to give you space weather warnings, who measure X-rays and protons, high-energy protons. To balance that set for predictive purposes, you need 47 flares that don't have an SEP event, because you want to teach your machine to make a distinction between something that's going to be dangerous and something that is not. So we look at flares larger than M3.5, that's a level, with no accompanying solar energetic particle events in the same period, seen with the same instruments. And Sukaina was the first author on the paper and did very well. So how do we do this? Did I miss step one? Oh no, this is step one, sorry. Feature generation. So you look at the correlation coefficients between the ghost channels, between the X-rays and the photons, the X-ray photons. Sorry, the X-ray photons and the protons, which is called the vector auto-regression model. Basically, you just shift the two timelines and see how well they correlate as a function of the shift. You do that over an integration period, typically 10 to 20 hours prior to the event. There's a time lag varies, as the time lag varies between the two, that you can vary between the two series. And then we cross-correlate. We also cross-correlate the proton channels with themselves. That actually seems to be important. So you produce, for example, a label or a feature, what we call it, phi between soft X-rays, the P11 photon channels with 3 typical lag times, which is that correlation event. So you have for each of these calculations that you do, you get a number, a correlation coefficient. And those are the labels that you try to analyze. Now, how do you do that? There's a simple, we selected decision trees as a classifier. I get to that. What is a classifier? Classifier is an algorithm, a piece of software that you can teach, that teaches itself to sort data. So you want to know SCP, nowhere SCP. That's what you use it for. And it does that by making decisions based on criteria on the labels. So just like we would do it. So it'd say, okay, if the X-ray intensity goes above this level, then it's highly likely such an event will occur, otherwise not. So that would be, for example, your first decision here, and then you go further. A couple of steps, not too many because you don't have many data. So we take that as a classifier just because we can understand that. So a decision tree is a set of questions, the answer of which are data. And this is the important part. The program creates the questions, not you, not the student, not even the thesis advisor. So you just throw the data in and it will make your decision tree. The question that we asked is, will there be a larger than 100 MeV solar energetic particle event? Over 100 MeV protons are dangerous. Nice thing is, once you create this decision tree, you get physical insight. You see what the criteria are for splitting the data. So that's one reason I like this. So here's what happened. This was the question. This was the result. Only 3 questions in a row, right? 1, 2, 3. And the accuracy that Sukaina derived was a little bit better than UMASEP, which is a code that's currently used by NOAA and NASA. I left the S out, just on the first try. So the time-lag correlation between the proton channels is just as important as that between the X-ray and the proton channels as well. So this works. And what we also could find is that if you increase the number of training examples, your accuracy goes up. So this is the training accuracy is of course 100%. So you give the code some data to train up, and then you let it make predictions for the rest. But the result gets better if you have more data. At about 80 we stop, 2 times 47 is 84, because we don't have more data. But we expect that as we get more data, our results will get better. At some point it will level off, but we don't know where yet. Yes?
How accurate do you know the ions are proton dominant? I assume there are some.
Yeah, the other ions as well, yeah. They're just as dangerous.
What percentage do you know are?
At most a few percent. There's some iron and carbon and nitrogen and oxygen, but they get roughly the same energy, so lower velocity actually, because they have higher mass. Yeah. This is not like cosmic rays. These are probably accelerated in an electric field. Yeah. Say again? Electrons are, they actually go faster because they're so much lighter, but the lower energy, and they're not as much as a danger to the astronauts, but they do happen, yeah. Yes, exactly, yeah, correct. So NASA people saw me present this at a conference. They were very enthusiastic. And they gave us a contract rather than having to write a proposal. They just say, we want you to do this, and sole source contract, they can do anything they want, basically. And so we do that. So, and India went to Shrek, and NASA used them to work there for the summer, and they were very happy with her. Then Manolis is working on expanding the prediction window significantly. That requires forecasting of flares and CMEs with those of high energy protons. But right now we have maybe an hour or two warning at best, which is enough to get an astronaut to come back inside. But you want to know a couple of days in advance if you can. So those are goals for the future. Next step is bigger, benchmark data sets. It's a big thing in computer science. Most solar physicists and astrophysicists don't get it. So let me try to explain. A benchmark is a thoroughly cleaned, frozen-in, sensibly formatted, publicly available set of data that you can use your classifiers on, train your classifiers on. And why is that? Well, people produce a paper, says, I looked at 60 flares, these parameters, I found an excellent way of predicting flares for these 60 flares. And then now somebody else writes a paper on 100 different flares and finds something else is also excellent. How do you compare the two? They're different data sets. You don't even know if they massage the data sets. So what they do in computer science for all kinds of uses is have standard benchmarks that you can let your classifier loose on, and then you can actually compare the performance of different classifiers, different improvisations of them, and see which one is really best. And of course, we want to have the best for flare prediction. So it's a test bed for machine learning approaches. The other advantage is you can be a computer scientist, know nothing about solar physics, but you can use that benchmark to make predictions. You can't be really good at everything. That's why we have interdisciplinary groups, so you can work together and you can learn from the other. Berkay did an incredible amount of work on it. I don't know if he's here, but he's a research professor now in our group and in computer science. And the benchmark data sets were explicitly requested in the National Space Weather Action Plan. So we have now a benchmark for about 7 or 8 years worth of flares observed by the Solar Dynamics Observatory, and it has been submitted. And the solar physics referee didn't understand at all. Oh no, you have to have all the data, have all the flares included. No, we throw out the flares for which we don't have good data because you can't use them for a good prediction. For example, you need to know the data of the magnetic field from where the flare erupts. What if, by mistake, you're looking at the magnetic field data from a nearby active region instead of the one where it erupts? Your whole prediction algorithm will be fooled by that. So if we have any doubts about it, you throw them out. And the data set is not complete. So here is an overview of all the magnetic parameters we calculated. Those you can find in the literature. They all, in some way, measure the strength of the magnetic field and the strength of the currents, etc. The quality flags, we use time series, which is done for the first time. Not just instantaneous values, but series. And here's a really, so I mean, old already, but what you see here is the standard deviation of the time variation of the net current helicity. Now, nobody ever thought of looking at that, neither did we, but we just took everything we could get. Because you can be greedy if you use computers. So this is the variability of that signal of the current helicity. Current helicity is a measure of the current divided over the magnetic field strength. People have looked at that because that seems to be obvious to look at, not at the variation of. So the red ones are flares and the blue ones are non-flares. And there's really, this is a good first step in taking the flares apart from the non-flares. It's not perfect, of course, it never is. But it definitely, if you can find another one like that perpendicular to it, you're in business. And that's what Rafal's group is working on now. So what do we do in the cluster? We do content-based image recognition. Content-based means looking at the image and trying to get information from it, not from the label. So if you see a picture of the Eiffel Tower, it says Eiffel Tower below, that's how Google recognizes that it's the Eiffel Tower, from the label, not from the image itself. It's really hard to train a machine to recognize the Eiffel Tower. Strangely enough, a human can do it instantaneously, right? Solar event prediction, I talked about that. So that's our short-term focus. And long-term, we want to branch out, look at stellar data sets because there's so much data. And Rafael is branching out into medical and biological research. So he's leaving us behind. So there we are. The group was started in 2014 by Rafael and me. And it's been growing like crazy ever since. We have now, how many? 23 graduate students. One upcoming tenure track hire. And this is the Holy Trinity here of people who run that group. So now I'm going to something else. Enough of that. Helioseismic data. This is something I work with. Dibyen Nandi is a professor in India, in Kolkata, longtime collaborator of mine. You all know Sushant, right? He just graduated from here. And then we have Munoz, is a former student of mine, graduated in 2011 from Montana State, and they all worked on numerical simulations of magnetic fields inside the sun. Andres Munoz. So what we know from helioseismology is two things we think we know. The sun rotates differentially, and inside it rotates differentially too. And thanks to solar seismology, we can measure that in the convection zone. There's also this flow, which goes on the surface to the poles. And then there must be a return flow somewhere down there, otherwise you don't have conservation of mass. But the return flow hasn't been reliably measured so far, because it's just too small a signal. And you have the same in the north and in the southern hemisphere. In order to drive dynamo models, you need both. This takes care that the field reverses after 11 years. And the dynamo, the differential rotation, is what wraps up the field lines, works like an alternator in generating current. So we did these simulations, or Anders did that for his thesis, and he was able to reproduce the really deep solar minimum we had around 2011, which was the first to do that. It was a nice result. And here is a nice graphics that NASA made for us from those simulations. So this is the differential rotation. The yellow lines are the field lines, and the sunspot number is given so you can see you're going through the cycle. Okay, and this goes on forever. So this is a nice result, but it's not confirmed by observations yet because we haven't measured the return flow deep inside the convection zone. And there are people that say, no, the return flow is right below the surface, and the whole dynamo is really a surface effect. And they can make that claim until you have the observations. Now, it's going to be a while until we really measure the return flow, but there are other ways of doing that, and that's what Sushant does. The question was, where is the dynamo wrapping up? Where is that effect located inside the sun? And we expect also inside stars. So we look at the energy of the solar dynamo. The increase in magnetic energy is done by work done by the Lorentz force. And the increase, the decrease in magnetic energy, or the increase, can do by the Lorentz force, and that's exchanged with kinetic energy. This is how the alternator in your car works, and this is how any electrical motor works, in principle. Kinetic energy and electromagnetic energy are exchanged. And then there's some other parts that I won't mention here. So these are the exchange terms. There's fluid potential, there's Joule heating, there's Poynting flux, and these are the exchange between the two sorts of energy. And these are the ones we're interested in. So we want to see, when the magnetic field builds up, where does the kinetic energy come from, and the other way around. So it was possible to measure the torsional oscillation. And torsional oscillation in the sun is this, that you have these different bands that rotate at different periods because it's differential rotation. And you see when the field comes up that the rotation near the equator slows down. That's a known effect. It's been known for more than 30 years. And the equation and the rotation speed at higher latitudes speeds up. And we think that's energy being transferred, kinetic energy to magnetic energy to kinetic energy again, across the sunspot belt. And that's what Sushant measured first. And here you see the bulge in the V phi at different locations, 30 degrees, 60 degrees. So, and here's the energy content that he managed to derive using those equations in the torsional oscillations using gong data. So here is where a lot of energy is being released. And that's where the torsional oscillation is. So what we found, or what I should say what Sushant found, the solar dynamo derives its energy from differential rotation deep in the convection zone, just as we expected, but a lot of people had legitimate complaints about that because it wasn't observed. It was only theory. You tell a theorist this, they shrug their shoulders. Yeah, we knew that. Typical theory attitude, right? But I think it's important. We live in observational science, and you have to confirm your results. So this has been submitted now. This is part of its thesis. We'll see how it goes. Oh, I'm really moving. Good. I'm in time. All right. So the last part I want to talk about, totally different problem. So I talked about simulations, big data, and just old-fashioned data analysis. And something that has interested me for at least 15 years, and I've only had not much time to work on it. There's not a lot of money in it because it doesn't have any practical consequences. It's the faint young sun paradox. Now, any of you who follow Russell's lectures on stellar evolution, you probably know by now that the luminosity of a star, not just the sun, increases slowly, here it goes, as a function of time. So the sun entered the main sequence about 70% of its current luminosity, 0.7 here, if you put it at 1 here. And the reason is that hydrogen is converted to helium, which makes the average density per particle in the core larger, which makes the scale height smaller, so the core contracts, gets even denser, which both the density increase and the resulting temperature increase make nuclear reactions more likely, so the nuclear reaction rate slowly increases over time. And that's what we think has been happening. Now you can calculate what the equilibrium temperature of the Earth's atmosphere would be as a result of that faint young sun, 70% in the beginning. So from the very beginning, the temperature would have been very low, way below the freezing point of water. Now we have the greenhouse effect, which is a great thing, because without it we wouldn't be here, which adds about 20, 25 degrees to the average temperature of the Earth. If not, we'd actually still be frozen over. But life developed more than 4 billion years ago. There's plenty of evidence of liquid water in the early Earth. So what happens? Something doesn't work. Now, people have come with all kinds of explanations. One of them being, of course, an enhanced greenhouse effect. Turns out greenhouse effect is self-limiting at a level that's way too dangerous for us, but at some point it will stop even if we burn everything on this Earth. And other is heat from inside the Earth, from nuclear reactions. There are many possible, albedo can change, and so on. Many solutions have been proposed in the literature. So here is what the calculation is like. The luminosity incoming at the top of the atmosphere minus the part that is directly reflected by deserts and the poles, snow, is equal to 4 sigma times the equilibrium temperature. That's Astro 1010 level, although I would never ask him that, but it's about at that level. So here are what these parameters mean, and then the temperature of the atmosphere is that plus the greenhouse effect, which is about 20, adding about 20 degrees Kelvin. So I really get a rise out of most audiences by telling them that the greenhouse effect is a great thing. But what we know now from the Mars exploration, Mars had oceans too, several billion years ago. And this is what, with the current topography, what the ocean picture of Mars would be. The whole northern hemisphere below water, with a frozen pole here, and the southern hemisphere is at higher level. It's a very strange map, very different from Earth. But we know there was liquid water on Mars, plenty of it. So you have the same problem with Mars, faint young sun problem. And Mars only gets half of the radiation that the Earth gets per square meter. So that's even worse. So you can come up with different solutions for the two, or you can use Occam's razor and say there's one solution for both. The sun was just brighter. There never was a solar fainting sun. So if you do the calculation, the solar flux to the planet, to the upper atmosphere goes like the 6th power of the mass on the main sequence. So if you have a 5% more mass in the early sun, that gives you 30% more incoming flux, which is just what we need. So the required mass loss to get 5% off in 5 billion years is about 10 to the minus 11 solar masses per year. What we know now, the current observed mass loss is a factor 300 less. So that's not very promising. However, what about the past? What if it was way more in the past? People have looked into that, all given a negative answer. I tend to disagree. And one of the reasons is this is purely theoretical research, one of the few papers that I'm sole author. The rotational slowdown of the sun. We know that young sun-like stars have a rotation period of a couple of days. We know that the current rotation period is 28 days, and it's the same for other sun-like stars at the same age. So it's slowed down a lot. How does it happen? Well, there's a magnetic torque by the stellar wind that goes out. This is a 30-year-old result. It was actually done in Utrecht when I was a grad student there, not by me. That torque depends on the magnetic lever. How far out does a magnetic field control the solar wind, and then it lets it go, times the mass loss rate. The more mass loss, the larger your torque. So I did a back-of-the-envelope calculation. What is needed for with a reasonable magnetic lever, which is a couple solar radii at most, for mass loss rate to slow down the sun? Well, it's close to 10 to the minus 11 solar masses a year. Close enough because this is the back-of-the-envelope calculation. So hey, so this is what this magnetic level looks like. This is the sun at maximum, and the top of the magnetic influence of the holding on to the outflow is here at the top of these streamers. So it moves a few radii now. If you want to make it worse if you want to do it in the future, okay, it has to go all the way out to the orbit of the Earth with 3 times 10 to the minus 40 solar masses per year to reach the same slowdown. We simply don't see that. So 2 more slides, okay? So this is a great work by Erika Bonfitense, where she put the cycle period in years of dynamos compared to the rotation period in days for a whole bunch of stars. And what she sees is 2 branches. This is a inactive branch, stars that have very low X-ray activity. And these are very much younger, typically, very active stars with very high X-ray activity. And then here the sun is in between, doesn't belong to either branch. What's going on? Why? So, but you can say one thing. The active branch has a Rossby number of smaller than 1, and the inactive branch has a typical Rossby number of larger than 1. The Rossby number is the ratio between the convective turnover time and the rotation period. It tells you which dominates, really. So here convection dominates, here rotation dominates. And now, so this is what I propose. This is, you could at best say it's a hypothesis. So this is how the sun evolves over its life. Its rotation period will go down as a function of time. It will stay on the active branch initially, and then in a relatively short time, can still be hundreds of millions of years, it drops very much in cycle period and goes to the inactive branch, where the Rossby number is larger than 1, and then it works up again. And the sun is right halfway in that transition now. That's why it's so irregular. That's why we have Maunder minima with very low activity, and then all of a sudden very much higher sunspot cycles. So these stars would be in permanent Maunder minima, and these would have permanent activity. And this is what the transition runs at Rossby number about 1. So that's it. Now let me give a shout out to Fabian. So we're interested obviously in dynamos and other stars. And you can observe those with Chara. This is what the sun looked like on April 18, 1947. This is what Chara would see now for a nearby sun-like star. And once that they have done the upgrade, this is what Chara will see. See, that's really pretty good. That's quite amazing. So we could look at nearby sun-like stars and actually see the star spots there. And I'm really excited by that. I'll leave it at that. These are our plans for the future, but you can ask a question on that.
Time for some questions. Sebastian?
About the Carrington event, you said it's a 1 in a century. How do we know it's 1 in a century, not 1 in 1,000 years or 1 in 10,000?
You can make a graph of the frequency of solar flares as a function of their energy. And it's a beautiful power law. And it goes straight to the Carrington event at 100 years. And it even extends further down for flares that have been observed on other stars. With Kepler. Yeah, that's a good question. Oh, yeah, sorry.
On your supposition that the sun is going like this, why can't it, so the zig, why can't it be going a zag?
Because the rotation period goes down as a function of time. Stars always slow down as they age.
No, it was going down and then it was going up again. Wasn't it?
Yeah, maybe you'll just, yeah, you're right.
Go back to that. Yeah, that one.
Maybe it'll just stay where it is at the end, yeah.
It going up again then on your supposition.
Yeah.
Is that right?
That's possible.
The red line.
Yeah, there's actually no need for that. No, the rotation period has to keep on going down. I don't know how fast. There's actually,
And what is that red line?
which one, the third one?
There's only one red line.
Well, okay, well, 3 segments of it.
Yeah, 3 segments of it. That, I thought you said that was your supposition is what might be happening.
Yeah,
But the last part of it, the rotation is increasing.
no, the period goes up, so the rotation goes down.
Well, that's the period.
Yeah, the rotation period. So the cycle period would go up. That's what we expect. But this is a question of hundreds of millions of years.
Same thing would happen if it went this way.
Yeah.
Wouldn't it?
Well, it has to stay on those curves because,
Yeah.
Ah.
But start at the bottom of the lower curve, then go up, and then to the upper curve. Instead of a zig, a zag.
oh, it could go sideways, you mean?
No.
Just the opposite way.
Just the opposite way. Start at,
Start low,